Hello friends, I once again welcome you to the journey of Six Sigma, and at present I would like to remind you that we are in the major phase of DMAIC cycle and discussing various topics and issues specific to major phase. So today say as a part of lecture 22, we will see the fundamentals of statistics and try to appreciate the importance of statistics and some of the important issues. So let us begin with a very good quote. It is the mark of a truly intelligent person to be moved by statistics, and the quote is given by none other than the great scientist researcher George Bernard Shaw. So this quote says that if you believe in scientific decision making, then you cannot avoid the use of statistics, and exactly Six Sigma also emphasizes on the use of scientific tools and techniques. So if we see the recap, then we have talked about properties of measurement system, bias, linearity and stability, measurement unit analysis, types of gauge R&R study, variable type, attribute type. We focused mainly on variable type gauge R&R, and in that also we had three options: R, range gauge R&R, X bar and R, mean and average, and ANOVA. So we have studied in detail mean and average variable gauge R&R study. Now as a part of this lecture, we would like to see some of the basics of statistics. What is the difference between descriptive and inferential statistics, measures of central tendency and dispersion, shape of the distribution, numerical descriptive measure for a population. The most important theorem in the statistics, please remember, is the central limit theorem. So we will see this central limit theorem, and then the random variable, the concept itself is the base for all the statistical analysis, and we will try to appreciate the definition concept of random variable. So what is statistics? So statistics typically it is a branch, a science of mathematics, and it basically enables the organizations, departments, maybe entire economy to take the sound data based decisions and helps the people to appreciate, accept the decisions which are based on scientific analysis. Now if you see the overall domain of statistics, then it is divided into descriptive statistics and inferential statistics. If you look at the descriptive statistics, you have collect, organize, summarize, display, analyze. And if I look at the inferential statistics, this we will subsequently see. Then I would like to predict and forecast values of the population parameter. I would like to test the hypothesis about my particular assumption of a phenomena, and then I would like to draw the inferences based on my statistical analysis. So there are various methods of descriptive statistics. Typically we classify these into, say, finding measures of central tendency, mean, median and mode. Measures of dispersion, you have range, interquartile, say range or data set, variance, standard deviation. You have shape of the distribution, because usually many of the assumptions in statistical analysis we try to go with the normal distribution, but here say it is important to know that my data is coming from which kind of distribution, and even if it is normal, what is the shape. So we try to say check the shape of the distribution, and the concepts are skewness and kurtosis, and you can have graphical or tabular format, histogram, stem and leaf diagram, or display contingency tables, scatter plots and so on. So basically we have four different ways to describe my data and take the decision based on the descriptive statistics. Here you can see in the box that you can summarize the data using different ways and means. You may put it in table, or you may have the graphical description, or you can have a statistical commentary, and there are various ways by which the data can be structured and represented in a meaningful way that can help the manager, decision maker to see the phenomena in depth and understand the overall perspective of the problem under investigation and take the decision. So, when we say look at the inferential statistics, you have estimation of the parameters and testing of the hypothesis. These are the two broader domains of inferential statistics, and this part in continuation we will study in the coming lectures. So, now say various statistical measures, as I mentioned, we can just summarize like this. There is measures of central tendency, which basically targets to say check the mean central tendency of the process, and this you can do with median, mean, median, mode, and you have measures of variability. So, the bare minimum or very say preliminary measure is the range finding the difference between maximum and minimum. You can extend it to interquartile range, that will divide your data into quartiles. You can have variance, and when you take the square root of variance you have the standard deviation. You can use skewness and kurtosis as the shape of the distribution. So, we will try to basically focus on descriptive statistics as a part of this lecture and study all these different measures for presenting my data in a more meaningful manner and analyzing it with the help of some of the measures used in descriptive statistics. So, let us see the definition. Central tendency, when I say, is the extent to which all the data value they are grouped around a typical central value. So, suppose I am measuring the diameter of the shaft, and suppose let us say my mean value, central value is 10. Then I am taking number of readings. Obviously, all reading will not be 10 because there would be certain process variation. So, let us say I am getting 10.1, 10.3, 10.4, 10.2, 10.25 and so on. I would like to see that to what extent my data is close to the central value of interest, that is 10 in this case. So, the variation, second term, is the amount of dispersion or scattering of the values. So, same example you can see that you have minimum value may be 9.8 and your maximum value may be 10.4. So, your data range is typically between 9.8 to 10.4, and you would be interested to see that what is the variation I am getting because of this process, and this is specific to variability. Then the shape, typically it is pattern of the distribution of values from the lowest value to the highest value. So, we will see all this with the example. So, you have arithmetic mean or average, and here we have already gone through the concept of population and sample. You draw the sample from the population to make certain conclusions, inferences based on say measures of central tendency, dispersion or inferential statistics. As it is not possible for me to focus on entire population, I go by the sample and related statistics. So, if you have a mean, usual practice is that you represent your mean as mu, and it is basically the summation of sigma xi I is equal to 1 to n, and you divide it by the total number, that is capital N, and if you have sample mean, then you have x bar equal to sigma I is equal to 1 to n xi divided by small n is your sample size. Now, just see the example, very simple. I have just put some sales data and I want to see that what is the average sales, mean sale that is taking place in the last couple of months. So I have just summed up my sales data. The sum is 320. I divide 320 by 20, that is the total number of data in a sample, and I get average X bar, that is 16. Now the second important say measure of central tendency is median. I am using again the sales data and I am just sorting it out in the ascending order. So in the initial first column you have the data which is not sorted. In the second column I am just putting it in the ascending order, lower value first and then the higher values. So now median is basically the middle value of the data sorted in order of magnitude. So higher magnitude I have sorted, and basically it is the 50th percentile. So here if you see, then you have 20 data point, exactly 10 can be divided. I am not getting exactly one say middle value, so I can take the average of two middle values. So in this case it is 16 plus 16 by 2, so I will have median equal to 16. Now the third measure of central tendency is mode, and mode is basically the highest frequency value. So the particular value which is occurring maximum number of time, highest frequency in the data set, I will consider that as the mode of my data. So if you see the example here, then I just put my data in the ascending order ranging from 6 to 31, and I am just putting the frequency in the form of a dot, that how many times particular number, you can say that these numbers are the sales or maybe the demand. So I am just counting the number, how many times it is occurring in my data set, and I can see that 18 is occurring maximum number of time. So mode of this data is 18. Now the other say way to look at the descriptive statistics is to check for the variability, and variability measures basically includes range, that is the difference between maximum and minimum value, interquartile range. So you divide your data set into quartiles and take Q3 minus Q1, we will see the example, that would be your interquartile range. Variance, average of the standard deviation from the mean. So how much my data values are varying with respect to mean, that is my variance, and simply when I take the square root of the variance, it becomes my standard deviation. Just look at the data set, and once again I am going with the first column sales, second column sorted data, the data is put in the ascending order, and you can say that 7 is the minimum and 28 is the maximum. So the difference is 28 minus 7, that is 21. Interquartile range, here what you need to do? So IQR typically is a measure of variability, again based on the dividing a data set into quartiles. So typically you consider 25%, 25%, 25% and 25%. So I can divide my entire data set into 4 quartiles, 4 parts, and typically what you say that each part is called first, second and third quartile. So typically I will denote these as Q1, Q2 and Q3, and Q1 is the middle value in the first half of the rank order data set. We will see the example, so it would be better clear. Q2 is the median value in the set, and Q3 is the middle value in the second half of the ranked data set, and when you take Q3 minus Q1 you get the interquartile range. So just see this example. I have the numbers 1, 3, 4, 5, 5, 6, 7 and 11, and what I can do, I can first find the Q1 which is the middle value in the first half of the data set. So there are total 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 data in this particular data set, and I would try to find Q1, which is the middle value. So, if I just partition it into 4 data, I am not getting the exact middle value. If it would have been the odd number 5, then I will get 3 as the middle value. But here let us say 1, 3, 4, 5 is one set of data, and 3 and 4 they both become middle value. So, I take the average of this 3 plus 4 by 2. So, Q1 is 3.5. Similar way, Q3 is the middle value in the second of the data set. So, my second of the data set is 5, 6, 7 and 11. So, similar way I will take the average of 6 and 7. So, 6 plus 7 by 2, my Q3 is 6.5, and your interquartile range is basically 6.5 minus 3.5, 3. So, this will give you an idea that what is the overall variability in your data when you look at the Q3, that is the last 25% of the data and the first. So, what is the difference and how the data is basically spreaded. Now, if you see the range, interquartile range, and then third measure, which is the variance and standard deviation. So, here typically each particular value of the data set is compared with the mean value. So, x minus mu or xi minus mu divided by n. When I use this expression sigma I is equal to 1 to n xi minus x mu whole square divided by n, I have used mu, and this is my standard, this is my variance for the population. When I take the square root, it becomes standard deviation. Similar way you can do it for sample. I am just putting here n minus 1 instead of n. We will see the logic later on, but in order to say go by or comply with my central limit theorem, and also because I am dealing with the sample, overall variability captured by the sample obviously would be on the higher side compared to the population. I am dividing this by n minus 1. So, sigma xi square minus sigma I is equal to 1 to n xi square divided by n, and n minus 1 say is the denominator, and s is equal to square root of s square, that is the standard deviation. So, I have a data set and x is 6, 9, 10, 12, 13 and so on. I am taking x minus x bar or xi minus x bar for various data, and then I am taking the square of it. So, you will have all the positive values. I am taking the x square, and then I am just trying to plugging the values in the expression of s square. So, you will see that my s square comes out to be 19.923 and further numbers, and you put your values in this expression. So, you will get 19.923684. So, you have s is equal to square root of s square, that is 4.46. So, this is my typically say standard deviation of the process. So, how much variability is there in my process is basically depicted by the standard deviation and the variance. Okay. So, now let us move ahead, and we have the display. We want to appreciate that actually when I say s is some number, what does it mean and how should I really compare. So, you just see the data set A, data set B and data set C. The data set A has a mean value 15.5 and S is 3.338. Data set B has mean value 15.5, S is equal to 0.926, and data set C has a mean value 15.5 and S value 4.570. Now, there is one thing to observe, that all the data set they have same mean value, that is 15.5, but your standard deviation or variance, if you take the square, associated with each particular data set is different. So, your data set A, if you observe, and I have just put the frequency, that how many times a particular number is occurring, then it has very large variability associated with the data, and that is 3.338. But data set B has same mean value. If I look at the S, 0.926, so your data is very much centric towards your mean value, and hence the variability is less. But if you see data set C, some data you have on one extreme, some data you have on other extreme, and this is exactly reflected in S is equal to 4.570. So, this particular display would help you to understand that if I am analyzing different processes in Six Sigma, then my process may have, various processes may have same mean but different variability, and the process which has much higher variability needs to be corrected and controlled, otherwise at any point of time it will start producing the defective items. So, this is the important part about variability, and you can further see here, we are talking about the Six Sigma. So, just see the first particular say your distribution, typically bell shaped normal distribution, and you will say that it has a larger standard deviation. When I see the second one, which is more centric towards the central value, you will say it is a smaller standard deviation, and this particular process which has a smaller standard deviation can help you to achieve the better sigma level, 5 sigma, 6 sigma, and this is exactly what we are trying to achieve through DMA IC cycle. Now, I would just like to focus on couple of more measures which are just the derivative of some of the fundamental measures we have studied, that is mean and variability measures. So, there is an important measure called measure of variation. So, this measure of variation is explained as coefficient of variation, typically CV, and it measures the relative variation. So, we have seen that the process may have, various processes may have same mean, but the variability is different, and the process with very high variability is considered a poor process. So, here just same thing is reflected in terms of ratio, that CV is equal to S divided by X bar into 100%. I want to check that what is the percentage variability with respect to my mean value. So, just see the example. Here the example is very simple. Suppose I am analyzing 2 different or 3 different or 4 different stocks, and let us say there is stock A which has average price last year $50 or some rupees, standard deviation 5, and I am just trying to find out what is the percentage variability with respect to mean. So, 5 divided by 50 into 100 is 10%. Same way you see the stock B which has average price last year 100 and standard deviation I am keeping same 5, so it is 5%. And then if I see the stock A and C, then stock A has 10%, C with high say average and higher lower standard deviation, it has 25%. So, what you can reveal in the first case, you can say that both stocks have the same standard deviation, but stock B is less variable relative to its price. In this case, what you can say, that stock C has a much smaller standard deviation but much higher coefficient of variation. So, please try to understand, many a times when we do not check it with respect to mean and this ratio, we may get misguided if we just look at the mean value or if we just look at the variance. Here you can very well see that stock C has a much higher coefficient of variation with some value of mean and your standard deviation. So, now the issue is that how can I establish the relationship between mean and the standard deviation. So there are some simple procedures and rules to follow in order to set the relationship between my mean and the standard deviation. So number one is Chebyshev's theorem and number two is empirical rule. So Chebyshev's theorem, typically it applies to any distribution and regardless of the shape. So I am not very much sticky about the shape, it could be applied to any kind of distribution. Now in Chebyshev's theorem, what it does, it basically places the lower limits on the percentage of observations within a given number of standard deviation from the mean. And when you look at the empirical rule, then typically it is applied to mound shaped or symmetric distribution like normal, and specifically approximates the percentage of the observation within a given number of standard deviation. So plus or minus k sigma with respect to mean I am trying to find out. So just see this Chebyshev's theorem, you have the rule like this, that regardless how the data is distributed, let it not be normal, not symmetrical, 1 minus 1 upon k square into 100% of the value fall within k standard deviation of the mean, for obviously k is greater than 1. So you can just see the numerical example, 1 minus 1 by 2 square into 100%, 75%. So my k value is 2. So I would say that 75% of the data set falls within mu plus or minus 2 sigma. Similar way, if I assume k is equal to 3, then 89%. So my 89% of the data set, typically they fall in the range of this. Now you would say, what is the need of finding this? You just think about demand data, you just think about product specification. You will find that you would be interested to find that what is that number, maybe consumer, maybe demand data, that would fall in a particular range, and you would definitely like to focus on that for developing a product, for developing a marketing strategy, for satisfying the customer, and finding this range is very important, and hence the establishing relationship between mu and sigma. So this another example can also further help you. So if I take k is equal to 2, 75%, if I take k is equal to 3, 89%, 4, it is 94%, and this is 2 times standard deviation of the mean, 3 times standard deviation of the mean, and 4 times standard deviation of the mean. If you look at the empirical rule, it applies to the symmetric distribution like normal, and we say that approximately 68% of the data fall in bell shaped distribution, normal distribution, when I say mu plus or minus 1 sigma. When I say mu plus or minus 2 sigma, it is 95% data, they fall in this range, and plus or minus 3 sigma, which is a widely used range, 99.7%. So this is where you can see pictorially that what exactly I mean to say in the empirical rule, plus or minus 1 sigma, 2 sigma, and 3 sigma, and you have say 1 standard deviation from the mean. Just the summary, 68%, 2, 95%, 3, almost 99.7%, and this. Now another important dimension is the shape, and we talk about skewness and the kurtosis as a part of the shape. So typically skewness measures the amount of asymmetry in a distribution, and kurtosis typically talks about the pickedness. So we have the different variety when we talk about the shape. So skewness, it may be skewed to left, unskewed, right. Kurtosis, you may have relatively flat distribution, you may have normal, you may have relatively picked, and these are some of the examples that says that left skewed, symmetric, right skewed, and you have mean is equal to median in the central case, mean is less than median, median is less than mean, and so on. Some of the examples I have put it for your say I have put for your self study. Skewness, then another example, skewness where all three are equal, mean, median, and mode. You have mode less than median less than mean, that is skewed to right, and as a summary you can see that various ways you can present the skewness. Okay, so shape of a distribution, typically we talk about the kurtosis, and you can see that you can have a flat shaped, bell shaped, which is typically a normal symmetric, and sharper peak. So typically it is a bell shape than the bell shape which has a sharper peak. So kurtosis I am just presenting in the form of say histogram, and you can see that it has more or less flat distribution. You can see that it is called mesiokurtic, and it has not too flat and not too peaked, so maybe very close to normal, and this you can see that it is a peaked distribution. So once again you will have the question in mind that what is the need of presenting my data in this form. So again I would say that basically I want to see that how my data is distributed, whether it is symmetric, whether it is going high in one value or it is skewed on left side, right side. So this kind of information can really help me to understand. Suppose I am talking about the case of sales data, and if I take the 12 month and if I plot my say data, it would give me immediate an idea that fine in which month or in what are the couple of months in which the sales is maximum and how the data is distributed. The another important measure is covariance. Whatever we have seen so far is mainly with respect to one data, let us say sales data. But don't you think you would also be interested to check that sales of, let us say, wafers, how it is changing with respect to the sales of the cold drink like Pepsi. So maybe you can assume another variable, that suppose sales with respect to, let us say, season, and you would try to study that how the variables they are associated. So here you can say that you have two numerical variables x and y, and covariance is x and y. So maybe in manufacturing setup you can say that you have set of operators and their skill, and then you have the output. So is there a relationship between these two variables? So you can check it by using a very simple expression, I is equal to 1 to n xi minus x bar, that is the first variable, and yi minus y bar divided by n minus 1, because we are using the sample. So you can interpret, if covariance of xy greater than 0, x and y tend to move in the same direction, x increases, y increases. If they are less than 1, then x increases, y decreases, opposite direction. If 0, there is no relationship, they are just independent. There is another important measure which is called coefficient of correlation, and typically either it is described as R or rho. So R is equal to covariance of x and y, again I am talking about two variable, divided by standard deviation of x and standard deviation of y. We have already seen how to find Sx and Sy, and when you plug in the values in this, you will get covariance of x and y. So typically you can visualize that covariance can vary from -1 to 1, and if it is closer to -1, then strong negative relationship exists. If it is 0, then very closer to 0 rather, very weak linear relationship exists, and if it is closer to 1, then a positive linear relationship you can predict between two variables. So this is just the example with various R values. In first case it is R is equal to, say this case R is equal to -1, so there is a negative relationship. Here R is equal to -0.6 negative relationship, but it is data is more scattered, so not a strong relationship. So basically it talks about the strength of the relationship. R is equal to 1, positive strong relationship, data is not scattered, your say line is covering all the data. When you see this, R is equal to 0.3, So there is a positive relationship, but your data is scattered and your line is only passing through some of the data set, and r is equal to 0. So there is no relationship between x and y. So typically you have numerical measures for a population as well as sample, and when I talk about the population, I have to consider the population, standard deviation and mean and variance, and this is the way we try to write using the mean and the capital N, that is the population size, to find the mu value and the sigma square. So many a times I would mention that we are not aware of the population variance and mean, and then we have to go with certain assumptions that we will see later on. So here we are going by the assumption that you can find out the population mean and the variance. So typically your notations are like this. If it is for population, mu, sample x bar, variance sigma square, s square, sigma and s, and central limit theorem, which is the most important theorem in statistics. I would just like to give you the details of this. So if all possible random sample, you are taking the different samples, each of size n, suppose you are manufacturing a bearing and you are taking 10 samples, each sample consists, let us say, 50 bearings for the measurement. Now each sample having sample size n is taken from any population with a mean mu and standard deviation sigma, that is about population, sampling distribution of the sample means. So you take the mean of each particular sample having 50 bearings, you are measuring the outer diameter, then you will have mu x bar is equal to mu. So the mean of your sample mean would be very much close to the mean of your population. And now I would like to remind you that here standard deviation sigma x bar will be sigma divided by square root n. So when I want to find the standard deviation of my mean sample, then sigma is the population standard deviation should be divided by square root of n and be approximately normally distributed regardless of the shape of the population. Your population may have triangular distribution, it may have exponential distribution, we will see couple of distribution in the next class, but your sample will have normal distribution typically when your sample size n is larger. So this is the crux of central limit theorem, and it is the central concept in the domain of statistical and probability theory, and typically it helps because many of the distributions can be approximated to normal, and normal distribution is the most convenient, easy to deal with, and this is where the central limit theorem plays an important role. Before we complete and conclude, the important term on which the entire statistics probability theory is based, I would like to share random variable, and typically it is a variable whose possible values are numerical outcomes of a random phenomena. Suppose you toss a coin or you roll a die, you do not know, there could be a chance of getting head and tail, there could be a chance of getting 1, 2, 3, 4, whatever. So broadly you have random variable which is an outcome of a random phenomena, and you have discrete means specific value, or you have continuous, it can fall in a particular range, maybe 10 to 11, 10.1, 10.4, 10.7, and these two are the different say types of random variables. So before we finish, as a part of our practice, I want to float couple of questions for your introspection and recap. So what is the difference between descriptive and inferential statistics? What are the measures of central tendency and the dispersion, and what do you reveal from this? What is its importance? What are the measures of shape and distribution? What is its utility? And suppose I give you a case that a person running a garment shop, suppose in a shopping mall, he wants to keep the optimum inventory of shirts which can improve his financial investment. Suppose you are not able to sell the shirts, then this inventory is lost or it will become obsolete. Now in this case, what do you recommend as the appropriate measures of central tendency and dispersion that he should use in order to have the better decision making on inventory keeping? So these are the references you can use: Azell, Levin and Kubek, TM Kubek, Michael Kuttner. So this will help you to appreciate the concepts in detail. So as a summary conclusion, statistics presents a rigorous scientific method for going insights into data, helps in classifying, organizing and summarizing, and it plays a vital role in every field such as business, banking, administration, manufacturing and all. So thank you very much for your patience in learning the concept, and I hope this preliminary understanding will definitely create a base for understanding the other statistical concepts in the subsequent lectures, and keep revising all the concepts. We are discussing the major phase of Six Sigma. So be with me, enjoy.